section, I would like to define the 6 trigonometric functions. So I know you've worked hard to memorize the unit circle. You suffered through all of the building. You know exactly where everything on the unit circle comes from, why all the angles are named what they are, what all the point values are on the unit circle from x squared plus y squared equals 1. Now we want to use it for something. And so what I'm going to define for you now are the 6 trigonometric functions. These are in no particular order, but it's always the order I put them in. I always put this one first, sine. So the function is read sine. The notation is Sin of t. And then equals, that's the y value on the unit circle, okay? Now, I should say, when I define these trigonometric functions, I should say it's the trigonometric functions of the unit circle. In a later section, I'm going to give you a different definition for the 6 trigonometric functions, but it's not truly different. It's still the same definitions, but we're going to be dealing with triangles. And then in another section, I'm going to give you an even third definition of the trigonometric functions that is dealing with any circle, not just a unit circle. But right now, this is for the unit circle. So sine of t. Now, t is a real number in radians. It could also be in degrees, but basically it's your angle equals the y value on the unit circle. What else? Cosine. Cosine of t, abbreviated COS, and I read that, cosine of t, not times t, of t, equals the x value on the unit circle. Tangent of t, we note that as tan of t. This is the function notation, and it is defined to be the y value over the x value on the unit circle, but it is important that x is not equal to 0. If x is equal to 0, you get undefined as your answer. All right, and then cosecant of t. So cosecant, we abbreviate that in function notation as CSC of t, and that's 1 over the y value on your unit circle. So remember, sine was the y value. Cosecant over here to the right is 1 over the y value as long as y is not equal to 0. So we call sine of t and cosecant of t reciprocals of each other because sine is y and cosecant is 1 over y. Well, you know what? Cosine also has a reciprocal, and it is called the secant. And so the function name is SEC secant of t. Is defined to be 1 over x as long as x is not equal to 0. If it is, then it's undefined. Again, cosine and secant are reciprocals of each other because cosine is the x value and secant is 1 over the x value. And then the 6th trigonometric function is cotangent. And I'm looking at my stuff, and it's not cotangent at all. Hold on just a minute. Okay, there we go. Act like you didn't even see that. So cotangent is COT, and I read that cotangent of t, and it is defined to be the x value in the numerator and the y value in the denominator, as long as y is not equal to 0. Now notice that cotangent and tangent are also reciprocals of each other, because cotangent is y over x, and cotangent is x over y. Now let's use these definitions to actually or use these functions or the definitions of the functions to actually evaluate some angles. Let me show you. So our first problem here, use the unit circle to evaluate the following. So that's what we're going to do. It says cosine of pi over 4. Now what are the things you need to know to do this problem? Let me get my highlighter out for you. First of all, I need to know how cosine is defined. I've got it highlighted up here for you on the unit circle. So it says cosine of t, which is pi over 3 in this particular case, pi over 4 in this particular case, is the x value. So I'm supposed to go to my unit circle and find the x value for pi over 4. Well, I got to find pi over 4. So I come over here to my circle. Look, there's pi over 4, and then the x value is square root of 2 over 2. So that's my answer. That's all you do. You go to your unit circle, you find the angle, and then you write down the definition for that particular function. Okay, let's try it again. This time I'm going to the angle pi over 3. Okay, so pi over 3, where is pi over 3? Here's pi over 3, right here, right? Now, sine on the unit circle, if I go look at my definitions, sine is a y value on the unit circle. So at pi over 3, I'm supposed to put the y value, which is, uh-oh, my pen's not behaving right again. There it is, square root of 3 over 2. So, sine of pi over 3 is square root of 3 over 2. I also know my pen magically erased the other value that I had. Remember, cosine of pi over 4 was the x value in the unit circle at pi over 4, which is square root of 2 over 2. Now, once you pause it, and you work on cosine of 7 pi over 6. So first of all, right, I have to find 7 pi over 6 on my unit circle, and it's right here. I'm just going to circle it. There's 7 pi over 6, and cosine is the x value on the unit circle. So the x value at 7 pi over 6 is right there. It is negative square root of 3 over 2. So you see how this works? We can do this. Let's do another page of them. Okay, so I have secant of 7 pi over 6. Two things I need to know. I need to know the definition of secant. I'm going to circle it up here in purple. And I need to know where 7 pi over 6 is on my unit circle. And it's right there. Now, eventually, you're going to have this unit circle memorized. I just put it on the page here so we have quick reference. But I hope that you can do this without a unit circle right in front of you soon. So I go to 7 pi over 6, and I remember that secant is 1 over x. So this is going to be 1 over, and my x value at 7 pi over 6 is negative square root of 3 over 2. Now, I'm not allowed to leave my answer like that. This is what we call a complex fraction. So I need to invert this denominator and multiply. So this is equivalent to 1 over 1, if you like, times negative 2 in the numerator now over square root of 3 in the denominator. When I simplify that, that gives me negative 2 over the square root of 3, but I can't leave a square root of 3 in the denominator, so I must rationalize to finally get negative 2 square root of 3 over 3. That was a whole lot of writing for that problem. More space than I have. All right, let's try this again. So let's look at secant of pi over 4. So what do I need to know? First, I need to know the definition of secant. Well, we're sticking with the same function. Secant is 1 over x. Where is pi? Well, pi is living right over here, right? Well, secant's 1 over x. So that's going to give me 1 over, the x value right there is negative 1. Now what? I simplify, and I get an answer of negative 1. So that's all there is to that one. That one wasn't bad. Now in blue, let's try this again. And maybe I need to erase a little bit of all this that I have going on as scratch work. All right, tangent of negative pi over 4. So what do I need to know to do this problem? I need to know the definition of tangent. I just circled that, and I need to know where negative pi over 4 is. Now, if you go backwards, they're not labeled that way, but the angle pi over 4 right here, if I go backwards, is in the same location as 7 pi over 4. And again, I'm zooming, and I know why it zoomed this time. Because my pen wasn't selected. Actually, it was selected, but it unselected itself. So, all right, got my pen back, and here we are at negative pi over 4, and again, you go backwards around the circle, and this value right here is negative pi over 4, the same location, or quote, coterminal to 7 pi over 4. Now, tangent is a y value over the x value, right? If you need to write that down, do. My y value is negative square root of 2 over 2. And my x value is positive square root of 2 over 2. Two ways you can think about that. You can invert and multiply if you want, or you have the same value on the top and the bottom except for the negative. They cancel to give you negative 1. But if you invert and multiply, you will get there as well. And then for my last problem on this page, anyway, is tangent of pi. Now, tangent is defined as it was in the problem before. Tangent is y over x, but we're looking at the angle pi this time, which is right there. Tangent is y in the numerator, x in the denominator. Okay, my y value right there is 0, and my x value right there is -1. We know 0 divided by -1 is 0. So that's my answer there. But we're not finished with these problems. I'm going to flip to the next page and do some more. My suggestion is when I flip it over, pause the video, you work these out yourself, and then come back and check yourself. And speed me up so I'm not talking so slow. All right, brand new problems. Hit pause. Do them. Come back. All right, you ready? You got cosecant of pi over 6. Now, cosecant is defined to be, and it's worth writing this down every time, 1 over y. Okay? So, I'm going to say this is 1 over, and I've got to look up the y value at pi over 6. So, the y value at pi over 6, I hope you're starting to learn them, but it is 1/2, because you're going to have to know them soon. And if I invert and multiply, that's 1 times 2 over 1, which we know that is 2. So the final answer is 2. How about secant of negative pi over 2? Now, secant is defined to be 1 over the x value. Okay, well, my x value at negative pi over 2. Now, when you have a negative, you got to be careful. Negative means you go backwards, okay? So if positive pi over 2 is at the top, negative pi over 2 is down here at the bottom. Same place as 3 pi over 2, they're coterminal. And I'm doing 1 over x. Well, my x is 0. Uh-oh. Can't do it really, but you can by saying it's undefined. And when you say something is undefined, you're really saying you can't do it. Okay, but that is the answer, undefined. Okay, let's keep going. How about the cotangent of pi over 3? So 2 things I need to know. I need to know that cotangent is defined to be x over y. And I need to know the x and y value at pi over 3. Now, pi over 3 is top right. Okay, the x value over there is 1/2. And the y value is square root of 3 over 2. Now, you can't leave it like that. You got to invert and multiply. So that's 1 over 2 times 2. Ooh, I didn't like a 2 at all. The pen's getting mad at me. So this is 2 over the square root of 3. 2's cancel. That gives me 1 over the square root of 3. But you know what? I'm not allowed to leave it like that. I have to rationalize. I need to multiply by the square root of 3 over the square root of 3. It's going to give me a final answer of square root of 3. That is a 3, y'all, over 3. That's square root of 3 over 3. Maybe the pen will let me get by with one more problem. Then I'll start a new video. Okay, tangent of negative 5 pi over 6. So 2 things we got to know. We got to know tangent is y over x. And I need to know how to get to negative 5 pi over 6. Now, I have an easier way to handle these negatives soon, but we're not there yet. Okay, so negative 5 pi over 6. Negative means we go backwards around the circle. Now, if 5 pi over 6 was right here, going in a positive direction, then negative 5 pi over 6, I'm circling it for you, is going to be right there because you're going in the negative direction. So my y value is negative 1/2. My x value is negative square root of 3 over 2. Ooh, I hope you're listening and not watching. Okay, the negatives cancel. The negative divided by negative is a positive. Now I've got 1/2. I'm going to invert and multiply by that denominator. That's 2 over the square root of 3. Okay, because that was square root of 3 over 2. The 2's cancel, and I get 1 over the square root of 3. But we already know what happens when you get 1 over the square root of 3. You rationalize to get square root of 3 over 3. It worked just like the blue one right there. All right. Not digging my pen right now, so I'm going to have to stop my video, and I'm going to edit it, and it's going to just really keep going as far as you're concerned. But hopefully my pen will write better when I come back. Next, I would like to discuss the fundamental identities. So now we know the definition of the 6 trigonometric functions based on the unit circle. A lot of identities come from that. The first that I want to get into is the even and odd identities. If you'll notice here, the cosine and secant functions, and remember cosine and secant, even though I haven't shown you the identity yet, they're reciprocals of each other. If you remember, cosine is the x value on the unit circle, and secant is 1 over the x value. And these guys are even functions. What does that mean? That means when you plug a negative t into the function, the negative disappears. Let me give you an example of another even function, and you'll feel a little bit better about what I'm talking about. F of x equals x squared is an example of an even function. Why? Because if you substitute in f of negative x, that's going to give me negative x squared, and the negative times the negative is positive, which essentially means the negative just disappears. So you get the same value when you plug in a negative or a positive value. Now, what does that mean for what we have going on with cosine? Okay, now remember, cosine is the x value on the unit circle. Now, a positive inside here, positive t, means you're going around in the counterclockwise direction, okay? A negative in here means you're going around in the clockwise direction. So just for example, let me use a highlighter. Say we go to positive 5 pi over 6. Notice the x value there is negative square root of 3 over 2. Well, what if we go to, instead we go backwards to the same location, negative 5 pi over 6, which would land right there. Look at the x value. It's the same. It's negative square root of 3 over 2. So it doesn't matter if you have a positive or a negative in here, you're going to get the same answer as you would positive. So again, for positive 5 pi over 6, you get negative square root of 3 over 2. For negative 5 pi over 6, you get negative square root of 3 over 2, the same answer. Same thing goes for the secant function because it's defined to be 1 over the x value. Okay, now the other 4 trig functions are odd functions. Now let me explain what that means using a function you know, and I'm going to erase all my drawing and start over again. So a function you know that is odd is f of x is equal to negative x to the 3rd power. That's an odd function. Why? Because when you plug a negative value in and simplify it, that would be negative x to the 3rd, and I raise a negative 1 to the 3rd power, that gives me negative x to the 3rd without the parentheses. In other words, you get the opposite. Odd means opposite, okay, sign-wise anyway. So if I plug in a negative x, I would get the opposite of what I get when I plug in a positive x value. Now, what does that mean? Another way to think about it, back to the x to the 3rd, I'm sorry. If you evaluate f of 2, that'd be 2 to the 3rd, you get 8. And if you evaluate f of negative 2, that'd be negative 2 to the 3rd, of course, and you get negative 8. You get opposite answers. So the function sine, tangent, and its reciprocals cosecant and cotangent are odd functions. What does that mean? Let's go back to our example I did just a minute ago. Use my highlighter, and I'm just going to go around to a certain value on the circle. Let's say we go to 2 pi over 3 in the positive direction. Now let's do the opposite and go to negative 2 pi over 3, which would stop right there at the coterminal angle 4 pi over 3. Now, sine is a y value on the unit circle. Well, look at the y value here versus the y value here. They're opposite signs, and that's what we mean by odd. Now, why in the world would you need to know if a trig function is odd or even? Okay, I have a good answer for that. Remember the problem we did just a few minutes ago? I'm going to back up. There are no results here, but look at this. Check out this problem right here at the bottom. Tangent of negative 5 pi over 6. Now, to do that problem, we went to negative 5 pi over 6, and you had to know where that was compared to where positive 5 pi over 6 is. It's at 7 pi over 6, but backwards. But now that you know that tangent's an odd function, you don't even have to evaluate tangent in negative 5 pi over 6. What you could do instead is evaluate negative tangent of 5 pi over 6. Why is that better? Because 5 pi over 6 is right here on your unit circle. That's the function that the angle that you would use. And tangent is going to be the y value over the x value, and then the negative just hangs along in front of it. So you don't have to go backwards around the circle. You can always go forward around the circle. So let me go back to my even odd. There we go. If you're dealing with an even function, so for instance, and I'm going to do more examples in just a minute, but let's just say we had to evaluate cosine of negative pi over 3. Well, who wants to go negative? Let's instead know that that's an even function. For even functions, negatives disappear, and that's the same as evaluating cosine of pi over 3, which is so much easier to do because we know exactly where pi over 3 is on the unit circle. It's right there. And cosine is the x value, and the x value at pi over 3 is 1/2. See? This even odd stuff is great. Let's do some problems with that. So here I have two problems. I have sine of pi over 3, and then I want us to evaluate sine of negative pi over 3. Now you can do it the original way, negative pi over 3, or you can do it using even and odd. And I want you to do it using even and odd. Now sine of pi over 3, we've been doing those for a little while now already, right? Sine is the y value. The y value at pi over 3 is square root of 3 over 2. But to evaluate sine of negative pi over 3, I don't want to do it that way. I know sine is odd, which means the negative comes out front. And I'm going to evaluate negative sine of pi over 3. Look, we've already calculated sine of pi over 3. It's square root of 3 over 2. So my answer is negative square root of 3 over 2. Because remember, we pulled that negative in front. Telling you that's the way to go. Use even and odd. Don't go backwards around the circle. Okay, next problem, cosine of 5 pi over 6. How do I do that? I go over to 5 pi over 6 right here and evaluate the cosine. And cosine is an x value on the unit circle. So the answer to the first one is negative square root of 3 over 2. Now, I didn't mean to ask that, y'all. This is supposed to read, I've got so many errors in my PowerPoint. I'm sorry. That's supposed to say cosine of negative 5 pi over 6. Cosine is an even function. For even functions, the negative just appears. So instead, you're evaluating cosine of 5 pi over 6. Lucky for us, we have already done that. It's right here. It is negative square root of 3 over 2. So use your even and odd properties to either pull the negative out front for odd functions or make the negative just disappear for even functions. And then you can go in the regular direction, in the positive angle direction around your unit circle, and save yourself some brain power. Now I have the reciprocal identities. You know these guys because I've already mentioned it. Sine and cosecant are reciprocals of each other. Why? Because sine is defined to be a y value, and cosecant is 1 over the y value. So instead of saying y and 1 over y, you could just say sine of t is equivalent to 1 over the cosecant of t. On the other hand, over here to the right, I have the opposite. Cosecant of t is also 1 over the sine of t. So you're reciprocals of each other. Cosine, remember cosine is defined to be an x value. Secant is 1 over x, which means those two dudes are reciprocals of each other. Cosine of t is the reciprocal of secant, so I can say it's 1 over the secant of t, and vice versa. Secant of t is 1 over the cosine of t. And finally, tangent and cotangent are reciprocals of each other. Why? Because tangent is defined to be y over x. Cotangent is defined to be x over y, so they're just upside downs of each other. And you will need this here and there, so it is definitely good to know. How do you memorize it? The tangent and the cotangent may be easy. They are reciprocals of each other, but like sine and cosine are not reciprocals of each other. You'll notice that sine and cosecant are the reciprocals. And what I want you to remember is that s and s don't go together. Notice that's an s and that's a c function. They are reciprocals of each other. That's a c function and that's an s function. They are reciprocals of each other. So you won't have two s's together and two c's together. You see what I mean? So s and c's go together as reciprocals. The second identity, or set of identities that I want you to be aware of. And really, this is the third set of identities we've done. We did even and odd, reciprocal, and now quotient. Tangent of t is defined to be sine of t over cosine of t. Now, why in the world would that be true? Well, remember, sine of t is defined to be the y value. Try that again. Sine of t is defined to be a y value. Cosine of t is x value on the unit circle. And look, that is the definition of tangent. So instead of saying tangent of t is y over x, you could also say tangent of t is sine of t over cosine of t. Hey, that comes in handy sometimes. Cotangent of t. Remember, by definition, cotangent of t is x over y. Well, another way to discuss x is saying cosine of t, and y is sine of t. So once again, you have what we call quotient identities. Tangent and cotangent can both be written as quotients. Now let's put this in action. If sine of t is equal to 2/3, and cosine of t is equal to square root of 5 over 3, they want us to find the remaining trigonometric functions. Now, I know you're just learning what in the world the trigonometric functions are. There's 6 of them, right? So here's sine and cosine just given to us. So we need to find the other 4. And what are they? Remember, secant, cosecant, tangent, and cotangent. So first of all, we could use our reciprocal identities. So if I'm trying to find what is the reciprocal of sine? Remember, the s and c's go together. How about cosecant of t? So cosecant of t is the reciprocal of sine. So I just flip that upside down, and I know it's 3/2. It is that simple. Cosine of t is the reciprocal of secant. Remember, the s's and c's go together. So I know secant of t once again is the reciprocal of square root of 5 over 3, which is 3 over the square root of 5. Now, it's got an extra step because you're supposed to rationalize your denominator. So I need to multiply both the numerator and denominator by the square root of 5 over 5. And what that does is that gets rid of my square root in the denominator. So my final answer here is 3 times the square root of 5 over square root of 5 times square root of 5 is square root of 25, which is 5. Okay? Now, I found 2 of my trig functions. Let's change colors just to stay organized. Let's find the other 2. So what about tangent of t? Now, tangent, remember, is sine over cosine. It's right there in front of us. That's the quotient identity. So sine is 2/3. I'm waiting for that 3 to pop up. It's not. There we go. Divided by cosine is square root of 5 over 3. And then I invert and multiply. So that is 2/3 times 3 over the square root of 5. Now what's great about this is the 3's cancel, and I get 2 over the square root of 5. But we're not having that, are we? We've got to rationalize. When I rationalize that, that's going to give me 2 times the square root of 5 over 5. I didn't show you the steps in there because you know what to do. I was running out of space. Now I'm not finished. I've got to find cotangent of t. Bear with me as I write all over the screen. At the top of the screen, I'm going to write down my answer for cotangent of t. Now, cotangent of t is the reciprocal of tangent. So I could flip 2 square root of 5 over 5 upside down, but you know what that's going to do? That's going to give me a square root in the denominator. What if I flip this one upside down? That would just give me the square root of 5 over 2. Another option is I could use this identity, cosine of t over sine of t. And so I put the cosine on top, square root of 5 over 3, and 2/3 on the bottom, and I flip it, and that also gives me square root of 5 over 2. What do you think about that? Not bad, right? Okay, so let's talk about some more fundamental identities. I lied. We had one more example before I jump into more fundamental identities. Example E says, use an identity to evaluate. Now, you might be looking at this 2.1 inside here and think, that's not on the unit circle. And it's supposed to say like pi over 3 or pi over 6 or 4 pi over 3 or even 30 degrees. Couldn't it say that? It could. But you know what? You don't even have to know that to do this problem. If you'll remember, these are reciprocals of each other. So watch this trick. I'm going to rewrite this problem as sine of 2.1. Yellow is kind of hard to see, isn't it? And then times, okay, cosecant is the reciprocal of sine. And I'm going to change colors in the process. That's 1 over the sine of 2.1. And what can we do? So again, to get the green, I just use the reciprocal, the idea that cosecant of 2.1 is the same as 1 over the sine of 2.1. And since these are both the sine of 2.1, those cancel, and that gives me a final answer of 1. Isn't that neat? Now, what's important about this problem? Well, your angle inside has to be the same, right? These both have to be 2.1 or you can't use that cute little trick. If this was 2.1, this was 5.8, the reciprocal wouldn't do you any good in that particular situation. So you need them to be the same angle inside, and you need those to be reciprocals of each other. But if that's the case, then you can use that reciprocal identity and flip that upside down, and then the numerator and denominator will cancel to probably give you 1, just depending on the way the problem is written. All right, let's do another identity. The next fundamental identity I would like to talk about is the Pythagorean identities. If you'll notice, there are 3 of them. The first is sine squared of t plus cosine squared of t is equal to 1. And then you have 1 plus tangent squared of t equals secant squared of t. And finally, 1 plus cotangent squared of t equals cosecant squared of t. Now, I don't have all 3 of those memorized. What I do is I memorize the first one, sine squared of t plus cosine squared of t is equal to 1, and I have a way of manipulating that one to get the other 2. But first, let me explain where this first one comes from. If you'll recall, the equation of a unit circle is x squared plus y squared is equal to 1. You also will remember that x, the x value on the unit circle, is cosine of t. So I could write this as cosine of t all squared plus sine of t, because y is sine of t all squared, equals 1. One more thing, cosine of t all squared, like this. Another way I could write that is cosine squared of t. Whenever you see an exponent between a trig function and the argument, that really means the whole trig function is raised to that exponent, which means sine of t all squared could be written as sine squared of t, and that equals 1. I could also rearrange. I could put sine squared of t first and cosine squared of t second equals 1, and that gives me that first Pythagorean identity. Now what I want to do is erase that and show you how I can get from the first identity to the second one. So you'll see I just rewrote the first identity down, okay? Now watch this trick. I'm going to take all 3 of these terms and divide by cosine squared of t. Now am I allowed to do that? You know what? Turns out I am. It's just like when you take an equation and multiply by the same value on both sides or divide by the same value. Now, whenever you divide by a variable, you do have to be careful because there's the possibility that that gives you 0. But actually, for this equation that we have up here, it's going to be undefined when cosine squared of t is equal to 0. So it's okay. Okay. Now, sine squared of t divided by cosine squared of t. That's the same as saying sine of t times sine of t, because it's squared, over cosine of t times cosine of t. Now, sine of t over cosine of t, using our quotient properties, gives us tangent of t. And since there are 2 of them, because it's squared, it's tangent squared of t. Cool trick, huh? Plus, cosine squared of t divided by cosine squared of t, we know is 1. And then 1 divided by cosine squared of t, well, if you think about your reciprocal identities, 1 divided by cosine of t is secant of t. So if you have this twice, that's going to be secant squared of t. And you know what? That gives us the second identity. It's in a slightly different order. I have tangent squared first and 1 second, but you remember you can add in either order you want to add. It's called the commutative property of addition. So if you take your original Pythagorean identity, sine squared of t plus cosine squared of t is equal to 1, and divide every term by cosine squared of t, you get the second one. I have a trick for getting the third one, and it's just as easy. I bet you can guess what that is. Let me erase and start back with our first line. All right, so to remember to get from the first one to the second one, I divided everything by cosine squared. This time I'm going to divide everything by sine squared. So I'm going to divide by sine squared of t here. I'm going to divide by sine squared of t here. And finally, on the right side of the equation, also by sine squared of t. Well, where does that take me? Well, we know sine squared of t divided by sine squared of t is 1 plus. Now, cosine squared of t, remember there's two of them. It's cosine of t times cosine of t divided by sine of t times sine of t. Now, cosine of t over sine of t, we know is cotangent. But since this happens twice, that's cotangent squared of t. Finally, using the reciprocal identity, I know 1 over sine of t is cosecant of t. But I have it twice because sine is written twice down here, sine of t times sine of t. So that's going to be cosecant squared of t. And that gives me my third identity, actually in the same order. So those are the Pythagorean identities. On the next problem, I would actually like to use that for something. Now, the Pythagorean identities are very common to use in a trigonometry class. On this first test, it's not going to be used as extensively as it might be on the third test, and you'll see what I mean when I get there. But this is a common question. Notice we have sine squared plus cosine squared, and it's the same angle on the inside, right? So sine squared of pi over 3 plus cosine squared of pi over 3. Well, if you have one of these identities and you have the same angle, then that means that's just equal to whatever says it's equal. So sine squared of pi over 3 plus cosine squared of pi over 3 is 1. Now here's the thing. If these didn't both say pi over 3, if this said sine squared of pi over 3 plus cosine squared of pi over 4, we couldn't use the Pythagorean identity. We'd have to actually just evaluate each of those separately, square each of the answers, and then add the work together. But because it's the same angle inside, I don't even have to evaluate each of these. I just say, hey, that's 1. I'm using the Pythagorean identity. Or another example is I could say 1 plus actually, it's not really what I want to do. But what if I said this? Let me erase. Instead of starting the video over, just let me erase this. Okay? Better yet, let me really erase it. Here we go. Okay. What if I said this? If I said that secant squared of pi over 6 minus tangent squared of pi over 6. What is that going to equal to? Well, first of all, you look at this and you go, well, that doesn't look like any of them. But you know what? It sort of looks like the second identity. It's just not written that way. But notice what I did is I manipulated it. I could say secant squared of t and move the tangent squared to the other side and make it minus. And as long as I have the same angle inside, that is also equal to 1. Okay? Now, I promise you, if you calculated these, just using the unit circle and what we've learned, you actually evaluate secant of pi over 6 and then square it. And you actually evaluate tangent of pi over 6 and then square it. And subtract, you would get 1, I promise. But it's nice to use the Pythagorean identities because it makes it easier. All right, let's add to that fundamental identities list. We want to talk about periodic properties of sine and cosine. And here's what we know. Remember coterminal angles, you add 2 pi or you subtract 2 pi. So we know that if you take an angle and you add 2 pi to it, you get the same exact terminal side, which means you have the same values for your x and your y value. So if you take sine of some angle and add 2 pi to it, you're going to get exactly the same thing as sine of t. Or if you take cosine of some angle and add 2 pi to it, you're going to get exactly the same thing as cosine of t. So that's the way you can use the periodic property. Now, tangent and cotangent actually have a different period. They repeat every pi. So this was tangent and cotangent. So again, if you take some angle and you add pi to it for tangent or cotangent, then you can just ignore that pi value and evaluate tangent of t. Same thing, cotangent of t plus pi, you can ignore the pi value and just calculate cotangent of t. Now we can summarize all that up by talking about the repetitive behavior of sine, cosine, tangent, and they could include cotangent here as well. But sine of t plus any even value, this is important, any even multiple of pi, okay, so any even pi, then you can ignore the even pi part and just evaluate sine of t. Same thing for cotangent. If you have an even pi, say for instance 16 pi, you can ignore that and evaluate cosine of t. But on the other hand, for tangent, it could be any pi, not just an even pi, but any pi value, say 15 pi. Then you could just evaluate tangent of t. So for instance, if I ask you to find tangent of pi over 3 plus 21 pi, you can ignore the 21 pi part and just evaluate tangent of pi over 3. I'm not going to do that because I'm running out of space here and I've got other problems planned for you. But that's exactly how you could use this repetitive behavior of sine and cosine. Now here's a couple of problems I want to take a look at where we look at that repetitive behavior. Now 13 pi over 4, I know you don't recognize that from the unit circle. As a matter of fact, the biggest labeled over 4 we have is 7 pi over 4. But 2 pi over here is the same as 8 pi over 4. So we know this is bigger than 2 pi. And here's a trick. We could take 13 pi over 4 and just subtract 2 pi from that. But now how do you write 2 pi in terms of over 4? Well, you just double the denominator. 2 pi is the same as 8 pi over 4, right? If you ever know what 2 pi is, double the denominator, and there you can speak in the same denominator terms. That gives me 15 pi. No, it doesn't. It gives me 5 pi over 4. So, what can I do? Well, instead of evaluating sine of 13 pi over 4, I could rewrite that as the sine of 8 pi over, well, hold on a second. I want to write the 5 pi over 4 first, and I'll make it more clear. The sine of 5 pi over 4 plus 8 pi over 4, which is 2 pi, right? And instead of evaluating the sine of 13 pi over 4, I can ignore that 2 pi and just evaluate the sine of 5 pi over 4. In other words, you're dealing with coterminal angles, folks. That's all you're doing. And what is the sine of 5 pi over 4? Well, let's find 5 pi over 4 on our unit circle. It's located right here in the third quadrant. Sine is the y value on the unit circle, so negative square root of 2 over 2. That's how you can handle that problem. Okay? How could I apply that to the second question, cosecant of 13 pi over 4? Well, again, use that periodic property, but first, let's use the reciprocal property. This is the same as saying 1 over the sine of 13 pi over 4, right? Because that's what cosecant is. It's 1 over the sine of that same angle. Well, we already have done the work to know that the sine of 13 pi over 4 is the same thing as the sine of 5 pi over 4. This is 1 over the sine of 5 pi over 4. Uh-oh. Okay, so I'm still trying to get this right. It zoomed in like crazy on me. Okay, so this is sine of, and remember what I'm trying to write here is 5, excuse me, pi over 4. Listen, we've already figured that out too. That's negative square root of 2 over 2. So I have 1 over negative square root of 2 over 2. My next step is I flip and multiply. Now when I flip that, that's going to give me negative 2 over the square root of 2. But I can't leave my answer like that. I have to rationalize it. Y'all, I'm going to go to the top of the page. Negative 2 over the square root of 2 times the square root of 2 over the square root of 2 is going to give me negative 2 square root of 2 over 2. These 2's cancel, so my final answer for the second one is negative square root of 2. Okay, so we have a problem here, the sine of negative pi over 3 plus 144 pi. Now what we just learned is that the trig functions are periodic, and sine and cosine repeat every 2 pi. So if you add an even increment of pi, 2 pi, 4 pi, 6 pi, 8 pi, or you subtract an even increment of pi, then to your angle, you can just ignore that even increment of pi. What you're really calculating is the sine of negative pi over 3. Why? Because this angle is coterminal to negative pi over 3. So instead of calculating this big old angle and taking the sine of it, then you can just find the sine of negative pi over 3, okay? Now, this has to be an even multiple of pi to be able to do this. If it were an odd multiple of pi, I'd pull out one of the pi's and add it to negative pi over 3, and then I would be left with an even multiple of pi, okay? So we just use the periodic property to do that. Now I'm left with evaluating the sine of negative pi over 3. But you know what? If you remember, you don't want to evaluate a negative angle with a trig function. We can solve that problem. All 6 of our trig functions are either even functions, in which you can ignore the negative, or they're odd functions, in which you pull the negative out front. And sine is actually an odd function. So I'm going to pull the negative in front of sine. So I'm going to evaluate the sine, oops, there's my negative, the sine of pi over 3. Then what I'm supposed to do, I refer to my unit circle, and I find pi over 3 on my unit circle. I'm just drawing a little unit circle here and reminding you where pi over 3 is. And sine is the y value right there, and the y value right there is the square root of 3 over 2. So my answer is negative. Now, once you go to the unit circle, you don't write this sign anymore. You handled that operation by going to the unit circle and grabbing the y value. And so my answer is negative square root of 3 over 2. Final result. But we use 2 different properties to do that. We use the periodic property of sine, and we use the fact that sine is an odd function. Now at the end, I'd like to talk about some calculator problems. The thing is, we've got these standard angles on the unit circle, whether you consider degrees like 30 degrees or radians like pi over 6. But I can ask you to evaluate the trig function of any angle, like for example 2.3 that I have written right here. And you would need your calculator to do that. So here's what I want you to notice. All of these 7 different questions, they all have 2.3 inside, but only the last one is 2.3 degrees. So if you see just a numerical value inside without a degree symbol, that's radians. So for all of these, you need to be in something called Radian Mode. I'm just going to write RAD, where this last guy is in degrees. Now, different calculators get into these modes in different ways. But if I'm looking at a TI-30X right in front of me, you're going to see I'm going to write over here to the right, a DRG button at the top. And when you hit that, you'll see 3 different options. You'll see DEG, that represents degrees, RAD, which represents radians, and GRD, which is gradient. We're only going to use the first 2. And I need to be in Radian mode. So I arrow over to RAD and I push enter, and now I'm in Radian mode, and I can see that at the bottom of the screen. Now to evaluate sine of 2.3, on my calculator, I just hit the sine button, S-I-N. I type in 2.3. I don't have to close out the parentheses, but it always makes me feel better. And I'm just going to round this to 4 decimal places, 0.74, and I have a 5.7. Usually you don't need 4 decimal places, but I'm just trying to show you as much as I can within reason so we can compare answers. Okay, now some calculators you would have to hit the 2.3 first and then evaluate sine. You'll have to play around to figure out if yours is one you need to do that. The next one again, I am still in Radian mode. It says it on my calculator. I hit cosine, I type in 2.3, I close the parentheses and push enter, and that gives me negative 0.6663 if I round to 4 decimal places. It's really 66627 and it goes on, but I'm rounding. Tangent is also a button just right on my calculator. I type in TAN 2.3, I close out the parentheses, and I get negative 1.1192. And again, I'm rounding 4 decimal places. But now look at the next problem. It says cosecant. And you can look all over your calculator, but there's no cosecant living there more than likely. So I have to use my reciprocal function, okay? Now, I know cosecant's 1 over sine. So I can just type in 1 over the sine of 2.3. That is one option, okay? And when I do that, I do 1 divided by the sine of 2.3. I definitely want to close out my parentheses there, and I get 1.3410. There is another option. You can type in, I'm going to do it at the bottom right, sine of 2.3. So sine of, the crazy zooming is happening, so sine of 2.3, and then you can hit this x to the negative 1 key, and that will also give you 1.3410. And you could do that for secant right here also. You could, the reciprocal of secant's cosine, so you could type in cosine of 2.3, and then hit this x to the negative 1 key. Yours might say 1 over x or 1 over y key. It'll work. Or you could do 1 over the cosine of 2.3. And I get 1.5009. And it's negative. So negative 1.5009. I keep going. Cotangent of 2.3. Well, that's the same as 1 over the tangent of 2.3. Or you could do the tangent of 2.3 and hit that x to the negative 1 button. So if I do that, tangent of 2.3, and then I hit the x to the negative 1, push enter, I get negative 0.8935. If I round, that was a 4, 8, and it keeps going. Okay, and then finally, to do this one, be careful. You've got to change this to degrees. So to do that, I'm going to hit that DRG button that we talked about earlier. I'm going to arrow back to degrees and push enter. Make sure you push enter. And then I'm going to evaluate the sine of 2.3 by just typing in sine, hitting the sine button, 2.3, close out my parentheses, and I get 0.0401. And that is this last one in degrees. Notice that's nowhere near the first time we did sine of 2.3 when it was in radians. If you have any calculator issues or any other kind of issues, please do let me know. I apologize about the zoom-in problem and the pen problem. The remainder of the semester, you won't have that issue when you watch the videos, but these videos that I'm doing right here, I've just got a few technology issues that I don't have that problem with the other videos. So I hope you have a wonderful day. Take care.